Hello students, in the previous video we began with electromagnetic induction. What is electromagnetic induction? When the magnetic flux across a coil changes, EMF is induced. When the magnetic flux across a coil changes and EMF is induced. The induced EMF produces a current and flow of electrons, and that is called induced current. Now we also said that we can create this electromagnetic induction, induced current by two ways. One is by using a magnet or by using another coil, right? The coil, you call it as a solenoid, where the current is allowed to flow through. Yes, I have taken the magnet. Yes, and I have taken a coil. Now when I bring this coil into close it and then bring it inside, then what will happen? The magnetic flux across this coil changes, which induces an EMF. Okay, and that is inducing a current basically. Now also you can have another coil, and this coil will allow the current to flow through, and it will produce a magnetic field, and that will change across this coil and again induce a current. Yes, that is also a possibility. But now today what we are going to learn is Faradays laws of electromagnetic induction. What are the Faraday's laws of electromagnetic induction? So again we should go back to a small loop like this, right? And then I said that we connect a small bulb, right? This is again a physical model I am talking, and we are taking a magnet with north and south pole going into this, right? This, okay? And you will find that when the magnetic flux across this is changed or cut, then EMF is induced. The induced EMF, epsilon, you use the symbol epsilon, okay, epsilon. Epsilon is proportional to rate of change of magnetic flux. Rate means with respect to time. What is changing with respect to time? Magnetic flux. So rate of change of magnetic flux. So this is referred to as Faraday's laws of electromagnetic induction, the first law. But you will find that you also can say sometime epsilon is equal to d phi by dt, but there is a negative sign here. We have to be very clear about this. There is a negative sign, and so we say it's a negative rate of change of magnetic flux. We will study about why there is a negative sign. What is the reason for it, the value to be negative? This we will study the second one. So first law says the rate of change of magnetic flux induced is proportional to induced EMF. Yes, that's the first one. And the direction of the current is such that it opposes the cause which produced it. Again, listen carefully. Yeah, the first law is talking about the epsilon, the induced EMF, and the second one is giving the idea about the direction, which is negative. What it says? It says that the induced current is such that the direction of the induced current, yeah, it can be clockwise or it can be anti-clockwise. That depends on the direction of the induced current is such that it opposes the cause that produces it. Look at it, very strangely, very interesting phenomenon, right? I got a solenoid here, and I got a north pole here, and I am bringing this here like this, close to it, and it passes through it. Then what happened? Current is induced. Now who induces the current? The magnetic field, the magnetic flux is inducing, but the direction of the current is it opposes the cause that produces it. Physics and everyday life is so much close to each other. This is the magnet which is inducing the current, but the current is opposing the magnet. Yes, it's very different. In life, what happens, right? Our parents bring us up, yes, and we grow. As a small child, we hold our parents' hand and we turn around 16, 17. Then we feel, oh, we are independent, we are everything, we know everything. So when our dad or mom says something, what do you say? I know, you don't know, you are old, you are from old generation, you don't know anything. Yeah, I know everything in this world. Yes, what are we trying to do? When we are growing up, as we are growing up, we oppose the parents who really produced us. Yes, here as Faraday says that the induced current is such that it opposes the cause that produces it. This magnet is producing and this is opposing again. Yes, and that is the law of life. Nobody can change it. Even you can read Swami Vivekananda. Swami Vivekananda also says the same thing somewhere in one of his books, right? A parent always will be opposed by the child. Yeah, that is the growing up, the age. So we should have a maturity as a parent, and as a children, we also should have, yes, and maturity. Okay, we also can listen, nothing wrong, to elders' viewpoints and everything. They also have experience, right? They only created us. Yeah, they are God. Ultimately, they are God. They are what creation is all about, right? So let us move on to Faraday's laws of electromagnetic induction. So that is why there is a negative sign, and this is called Lenz rule. This is called Lenz rule. Okay, these are the two laws basically. If you talk about Faraday's two laws, whenever the magnetic flux across, that's the first definition is, whenever the magnetic flux across a coil changes, an EMF is induced, and the induced EMF is proportional to rate of change of magnetic flux, and the sign is negative, that is given by Lenz rule. It's called the Lenz rule, and now we will study more in detail about Lenz rule. I hope you understand the concept. Yes, Faraday's laws, and from where we move on to Lenz rule. We will study in detail. Yeah. See, we are now studying more in detail Lenz rule. Okay. See, before that we should know that the current will be clockwise or anti-clockwise. We know that a clockwise current represents south pole. A clockwise current represents a south pole, and an anti-clockwise, right? This is going in anti-clockwise direction, that represents a north pole. Yeah, so this is clockwise and this is anti-clockwise. Yes, now I take the loop here. Let us connect a small LED bulb. Take a magnet, north pole and south pole, magnetic field, and hence it cuts it, magnetic flux. Okay, now this is the north pole and this is the coil, solenoid. This is the solenoid coil. The area of the coil is there, right? So you have to imagine like a coin, right? This is written 1 rupee here, and there is a tail, and there will be back something, and that is called head. Okay, head and tail. Keep this in mind. It is like this, right? And it is not like this. You know, it is going to be 2-dimensional, here 3-dimensional. North pole I have taken. I bring the north pole here, and what will happen? As it is coming close, it is opposing. If it is opposing, what should be the pole of this? This also is becoming a magnet. This copper wire, the solenoid, this part also becoming a magnet. Then when I bring the north pole, this should become what pole? In order to oppose, it is opposing, repulsing. That means this is north pole, this should be what pole? North pole. North pole and north pole will repel. If it is north pole, what is the direction of the induced current? Anti-clockwise direction. Anti-clockwise direction. Do you understand what I am saying? Yeah. See, according to Lenz rule, it has to oppose, right? And it is opposing. Suppose if I take the south pole and I bring the south pole and this part, right? This part. Now, what will happen when south pole is coming? South pole, this part has to become south pole, then only south pole and south pole will repel. South pole and south pole will repel. When it becomes south pole, then the direction will be clockwise, right? You can take head and tail like this, and if you draw one more here, you call it as head. Okay, if it is a head, it is going to be north pole, and if it is going to be tail, you can say it is south pole. Yes, because it depends on what polarity it is going to become. Is it going to become south or is going to become north? This is what it is. Look at it very carefully. I am just taking a magnet and I am allowing it to pass through a wire, a coil, a solenoid, and current is produced. Boom! Current is produced. How can it be? How can it be? Is it obeying law of conservation of energy? Law of conservation of energy has to be obeyed. Now, law of conservation of energy has to be obeyed. Now, am I getting electricity out of nothing? No. We are getting the electricity because I am doing the work. The work I am doing is the mechanical energy. The mechanical energy transferring into the light energy or magnetic energy to light energy. Yes, it obeys the law of conservation of energy. Now, why it has to obey the law of conservation of energy? That is very common, natural. In order to obey the law of conservation of energy, now you see what's going to happen. I am bringing the north pole here, and if this becomes south pole, what will happen? If this is north pole and this is south pole, right, and if I take it like this, it is just going to come like this. It will get attracted. That means I need not do work at all. I need not work. I bring it closer, it just inserts it in. So, it cannot be so. It has to do, I have to do external work. For law of conservation of energy, I have to obey, right? And when I do the work, north pole, then this becomes north pole, it will oppose. When it opposes, what I will do? I will put more energy, and then I will push it. You understand? Yes. So, law of conservation of energy is obeyed in Lenz rule. So, what is happening? When this comes north pole, this becomes north pole. So, I need to work. That means I need to put energy. That energy is converted into energy. That is light energy. Mechanical energy into light energy. Now, look at it. Suppose if I take the magnet and I place it just inside the solenoid like this, yeah, do you think anything will happen? Nothing will happen. Nothing will happen. It will not produce electricity at all. It will not induce EMF at all. Why? No work, no energy, no current, no EMF. You get my point? You have to move it. The magnet has to move it. If it does not move, then electricity will not be produced. Be careful, right? Now I am pushing it in. This is north pole and north pole. Now look at it. I am pulling it back. I am pulling it back. Again, Lenz rule should hold good. The cause which produces it, it has to oppose. When I pull it, what it will do? It will not allow. It will say no. When I try to push it in, it is opposing. It is opposing, right? So that I have to do work. Now when I take it back and I pull it out, what it will do? This will become south pole. This will immediately turn into south pole. When it becomes south pole, what will happen? This is trying to attract. So I have to again do work to remove it out. Yes, what a complex concept you see. Yeah, but very easy, very interesting. You think of life. In our life, when my father says, Sridhar, go to college. What I say? No, I will not go to the college. Yes, I am negating my daddy's word. My father says, come on, today it is raining so much out and don't go out. What I say? No, I will go out. If he says yes, I will say no. And if he says no, I will say yes. Yes, this is negation. It is a not gate, right? So you say yes and say no. So what is happening? North pole is coming, this becomes north pole. It is opposing. Now, when I am returning it back, it turns immediately into south pole, and this is a fixed magnet. This polarity cannot change, but this becomes south pole, so that again it is attracting. So I need to pull it out. So the principle, law of conservation of energy is obeyed, and Lenz rule, that is why there is a sign epsilon is equal to minus d phi by dt, right? Rate of change of magnetic flux is inducing EMF, but it is always negative because it is opposing, because it is because of Lenz rule. And Lenz rule obeys law of conservation of energy, and try to understand the concept clearly, right? North pole, north pole. So look at it now, south pole in terms of south pole. This will become south pole, fine. Now I bring it back. This south pole is south pole, but this will become north pole, and try to pull it. So I need to do work to take the thing out. Is it fine? To take the magnet out. Fine. So this is what the Lenz rule is, and the concept of Lenz rule obeying the law of conservation of energy is proved using this experiment. Okay. Thank you so much.